Okay, so this is going to be my first vlog in this YouTube channel, where I'm going to be logging my journey as I learn more about physics through the Yale Physics 200 course by Professor Shankar that can be found online. Links to his videos will be posted in the description below, and let's get started. So the first thing we're going to learn about, or at least his first video, is about Newtonian mechanics, or specifically kinematics. Now, we have to first start with the concept that x is a function of time, where x is distance. If you take the instance of a car, right? This is a car, it's got wheels, where at 0 seconds it's at 0 meters, 1 second it's at 1 meters, 2 seconds 2 meters, and so on and so forth. You can see that it's moving along the x-axis, so we label that x. And it's moving through time as well, so we put in time. And so, if you're to graph this as x as a function of time graph, which can obviously be seen here, where because time went up by 1 second, the distance, or x, went up by 1 second. Time went up by another second, x went up by another second. So you can graph that, saying that x is a function of time where it is equal to time, and time is just the independent variable, so it goes on the x-axis. Yeah, kind of weird having x on the y-axis and something else on the x-axis, but you get used to it as you do physics. So, at 1 second, we're saying that the car was at 1 meters, and then 0 seconds, 0 meters is the origin. 2 seconds, 2 meters. And now you can see that we have a nice little line, right? Which makes sense. As time goes up, the distance that it travels will also go up, because, you know, it's equal to time. Now, what would the slope mean, like in a physical sense, in this graph? Well, slope is just rise over run. Okay, so you go up, which is your rise, and you go over to the side, which is your run. So your rise, if you think about units, your rise is done in meters, and then it's over your run, which is done in seconds. And this, in meters over seconds, is a unit in itself called meters per second, and we use it to measure speed, which we write as v. Now you can also write v as a function of t graph, or a vt graph, by using this concept. Right? This is a bit too long, but whatever. And you can also draw 1 second, 2 seconds, 3 seconds, etc. here. And then this is 1 meters per second, because that's what we're measuring v in, meters per second, and we draw it like that. Well, you can also write it like this, but that's unnecessary information. Anyways, so if you just look at this, the slope the entire way through in this particular situation is always rise 1 over 1, rise 1 over 1, etc. And it's always going to be 1, right? So if you're to draw a corresponding VT graph, no matter what the time is, the V is always 1, so it's just going to be a flat line. But what if it weren't always 1? What if you actually did have... Wait a moment, let me just mark a few more things along here. What if you actually did have a bit of a slope? Well, at 0, it's 0 seconds at 0. 1 second, it's 1 meters per second. But now we're moving on to 2 seconds, it's 2 meters per second. And 3 seconds, it's 3 meters per second. And I didn't quite draw this well, so it's not gonna look too straight, but you get the idea. If it were a straight line, like that, what would the slope in this case mean? Well, going back to units, if you go up 1, and then over 1, you're going up by meters per second, and then you're putting that over seconds again, and you once again end up with a new unit called meters per second, also known as meters per second squared. And we use this to measure acceleration, the speed at which you're speeding, if that makes any sense. And I'm not going to draw an acceleration versus time graph, because that would just, in this case, would just be a flat line across the thing as it was originally. But what we basically just did was we went from x, then we got to v, and then we got to a, right? Now, technically, in the x for this red line situation, let me color code this. So in the red line situation, first you went at 0 meters per second, right, at 0 seconds, 1 meters per second at 1 second, so you went 1 meters, but then at 2 seconds you went 2 meters per second, so you didn't go up another meter, you went up another 2 meters, right? And then at 3 seconds you went up 3 meters from where you were, so that would be something like here. And once again, if I can draw my line right, you can see that this one actually does curve. And this is intentional, not just a drawing flaw like it was last time. This is intentional. This means that, like, there, at any point in time, velocity is, like, constantly changing, right? So if you're to try and find the velocity at any one time, it's incredibly hard because, it's a curve. It kind of looks like this. You don't know how to find the rise over run of that. And this is where calculus helps us out, which basically says, and by the way, I do not know much calculus, if any. Like, I just barely understand the concept, but so you're just gonna have to bear with me here. If I mess up, I'll probably come back and look at this and go, oh boy, I messed up. But anyways, from what I understand, calculus is just says that if you zoom in on this, like, really, really tiny section, let's color it in blue, like this really tiny section. If you zoom in far enough, this curve eventually turns into a flat line. And once you have a flat line, you can just go up 1 over 1, right? And this concept of zooming in on a really small part of a line is called taking the derivative of it, because it's like the delta y over delta x, which is what rise over run is, by the way, but on a really, really small scale. So we just go, say, as, in this case, t, which is on the bottom, approaches 0, right? So we call this taking a derivative, and we write it as d, and then your variable that's up top. In this case, in the case of the xt graph, it's x. So you write, scroll down a little further. You write dx over dt. And that's what we did to get to v from x. And then from V to A, well, we also did the same thing. It's just that it's much simpler. But technically, we did still zoom in on a really, really tiny part, saw what the velocity was. It just happened to be the same all the way. Acceleration was in this case. It just happened to be all the same all the way through. And we did dv in this case over dt. But what if I wanted to get from x directly to a? Well, because I'm just taking one derivative and then another derivative, I can take what's called a double derivative of x, where we draw d squared x over dt squared. And time to delve into more calculus, which I probably won't be able to explain too well. Sorry, not understand. I more or less understand it. But what this is saying is your d squared x over dt squared must equal to a, right? Now, if you're to integrate this, and I don't want to try and explain integration quite yet, except for it's just basically trying to guess what equation in this case, if you're to take the double derivative of, would end up giving you a. I'm not going to explain the process, but in the end, you end up with x as a function of t. Ooh, just draw that a little straighter. I like my things to be a little straighter. That way it doesn't, go off diagonally. Anyways, you get this equation, at squared over 2 plus bt plus c. Now, so far it's only been mathematics, right? This has all honestly just been mathematics. It has nothing to do with physics. So, how can we relate this back to, well, physics? Because we're not doing a mathematics course, we're doing a physics course. Well, Professor Shankar does it in a really ingenious way. Now, through experimentation, scientists have found that close to Earth, this is Earth, objects in a vacuum always fall with the same acceleration, a constant acceleration. No matter what the object, as long as they're in a vacuum, they will fall at the same rate. Doesn't matter if it's like a textbook or, in this case, a brick and a leaf. Doesn't matter. They'll both fall really fast, honestly. So, in this situation where we have a constant acceleration, using this situation that we find in real life through experimentation, we can link it back to this mathematical formula, which requires us to have some constant acceleration. Remember, this thing does mean acceleration, right? So, using this this observed phenomena, we can say, is it a phenomena? Am I right in using that word? Whatever. We can say that this equation can describe the motion of an object near Earth. So let's draw Earth a little bigger. We can say that this equation can describe an object near Earth, let's say a ball, the position of it at any given time because of constant acceleration. By the way, this constant acceleration we call this constant acceleration g because it has a specific value, which is negative 9.8 meters per second squared. Now, because we can now tie the mathematics to the physics, because physics is something, it's a science, meaning that you have to see it experimentally and in the actual world. Mathematics, however, is a human construct that uses logic and is very axiomatic. Just straight up humans made math. So it doesn't actually have anything to do with the real world. It just happens to be that we can use it to explain the real world. Now, because we have now stated and shown that these two things are related, you can actually describe an object that's falling close to Earth with this equation. Though technically it's along the y-axis, so we just change this x to a y. Now that we've done that, we can now go on to explain what these variables. Let me just grab my eraser real quick. Oop. We can now explain what the variables b and c actually mean in a physical sense. Because we know x, which is position, we know a, which is acceleration, but we have no idea what b and c are. And without this link to what the fact that you can actually apply this situation, this mathematical formula, to a situation in real life, we wouldn't have ever been able to tell what b and c are. Okay, now that we've established the connection between the physics and the math, we have to figure out what in the world b and c mean, right? So I'm going to use two different situations to explain the two of them. If you take a situation where y of t, it's just another way to say position because it's on the y-axis this time rather than the x-axis, is at squared over 2 plus bt plus c. Honestly, I should have that on copy to clipboard. That way I can make it just appear whenever I want. Alright, back to this. Let's say you have an apartment building and a ball, that's a ball, is being thrown from some floor of the building. Building itself is 100 meters, but that's not really relevant right now. This is 0 meters, and this is the final y position it's going to end up at, right? We have a constant acceleration because we're close to Earth. It is an apartment building, and I don't usually see apartment buildings floating around in space unless you count the ISS, but that's not much of an apartment building. Anyways, so we have some constant acceleration a, which is our g, which we have a value for, so I'll write it down. Negative 9.8 meters per second squared. And the ball was dropped, not the dropped was ball. The ball was dropped from 80 meters up. Now, c we know is a constant, right? Because there's no time into it. Whatever c is, it stays the same. It doesn't change over time. Well, if you look at this 80 meters, the initial position that it was dropped from, it actually doesn't change over time. As at 1 second, it was still originally dropped from 80 meters. 2 seconds, it was still originally dropped from 80 meters. Doesn't change. So we call this the initial position. And in this case, we write it as y naught, with a little 0 subscript. And if it were on the x-axis, it would be x naught, as was the situation with if you can find it, the car. The 0 here, this thing, that was our x naught. Ooh, I seem to have that written in. Anyways, so this just proves our c value, right? Now, that's all fine and dandy. C is not that hard of a concept to understand. So now we can write it down as our y initial, or y naught. Let's also label our a as our g. But now we have to figure out what b is. So I'll take a different example. Let's say you're floating in space. This is you, not accurate representation, but this is more or less what you would look like. You have arms, one arm slightly longer than the other, well, twice the length, a head, body, legs. Anyways, you have you, and let's say you're holding a taco. Why not? I like tacos. You like tacos, probably, unless you don't, and that's fine. Tacos are nice though. And say you have a taco, and the catch is you're in space. And this is your space helmet. Right. You're floating through space. There is no acceleration, by the way, in space, because there's no gravity in space. In this case, right, there's no acceleration because we have no gravity. So this section of the equation, it actually ends up being 0 because 0 into t divided by 2, it's all 0. All you have is bt plus c. You know that c is your initial position. I should probably write that here. You know that c is your initial position. But you don't know what b is yet. Well, if you think about it, you have a taco, but you can't eat it. So what else can you do with it? You can do a lot of stuff, but let's say you want to throw the thing. When you throw it, you have to throw it with some speed, right? Otherwise it wouldn't move. And this speed, let's say 5 meters per second, the speed that you throw it with is multiplied into the time that it travels for. Let's say it travels for 3 seconds. And that multiplies out to give you your distance, because if you traveled at 5 meters per second for 3 seconds, it's just 5 for 1, 2, 3, and those all get added up, and you get 15. It's basic math, right? And you end up going, the taco ends up going 15 meters before smashing into a giant asteroid. Ooh, that's not an asteroid. Let's say this is an asteroid. It's real oddly shaped, but what can I do? Asteroids are asteroids. And it smashes into the asteroid. But guess what you did? You have the same situation as here, but A's part doesn't exist. You just have C. Now C is also non-existent here because you start at an initial position of 0 meters, so C is just 0 meters, and 0 plus anything, it just stays the same. That means you must have t, because this is in time, and the b segment of your equation left over. And basically this shows that your b segment is actually your initial velocity, what we call v naught, or rather initial speed in this case. So we can now label this b as our initial speed. And that's it for today. We've learned, let's do a real quick recap of what we've learned. We've learned that, if I can find it, there we go. We've learned that x is a function of t. We've learned how to get to this magical equation of, I've said it many times. I'm not going to say it again. You know what I mean. This equation, this magical equation. And we've related it to the real world through just an experimental fact, something that we've observed. We've defined what it means, and now we know how it works and how we can apply it. So, yeah, that's it for today. In the next video, I'm going to be using this magical equation to make my own physics engine within Unity. So go check that out once it comes out, or once it does. By the time you watch this, it probably will have come out. But go check that out if you really want to see how my journey as I try to make a physics engine from scratch in Unity. And see ya.